Modules and Homological Algebra, Lecture 23, One-Sided Exactness. Let us start by a quick recap what an exact functor is. Let R and S be two rings. Consider the categories of all R modules and of all S modules. Let F be a functor from the category of all R modules to the category of all S modules. Recall, a functor f is called exact, provided that it sends exact sequences of R modules to exact sequences of S modules. Now, let us note that any exact sequence can be considered as gluing of a certain short exact sequences. So if we have an exact sequence which consists of components xi minus 1, xi plus 1, and so on, and the differential is fi minus 1, which goes from xi minus 1 to xi, fi, which goes from xi to xi plus 1, and so on, then this exact sequence can be considered as the gluing of the following short exact sequences. So we take the image of fi minus 1, which coincides with the kernel of fi, we include it into xi, and then we have the map fi, which sends xi to the image of fi. And this is a short exact sequence because the original sequence is exact. In general, we have the following commutative diagram. So here, in the first row, we have the original exact sequence of xi's and differentials fi's. And now we write here the image of fi minus 1, the image of f of I, and so on. So starting from xi minus 1, we use fi minus 1 to project it onto the image. And now we take this image and we include it into xi. And then from xi, we go by fi onto the image of fi. We include it into xi plus 1, and so on. So here we have at each position the short exact sequence of the image of fi minus 1 included into xi and then projected onto the image of fi. And our original exact sequence is a gluing of these short exact sequences. In particular, it follows that a functor is exact if and only if it is exact on short exact sequences. And the aim for today is to discuss two natural relaxations of the condition to be exact on short exact sequences. So we start with the notion of a right exact functor. So let f be a functor from R mod to S mod. Definition: we call f right exact provided that for any short exact sequence of R modules, so 0 goes to x, then by alpha to y, then by beta to z, and then to 0. For any such short exact sequence of R modules, the following induced sequence of S modules is exact. So we have f of x, then f of alpha going to f of y, f of beta going to f of z, and this goes to 0. Note that in the second sequence we do not have this leftmost 0. So when we say that this sequence is exact, what we really mean is that it is exact in the positions of f of y and in the position of f of z. There is no requirement on the behavior of f at the position f of x. We define left exact functors in a similar but dual way. So let f be a functor from R mod to S mod. Definition: we say that the functor f is left exact, provided that for any short exact sequence of R modules as follows, so 0 goes to x, then by alpha to y, then by beta to z, and then to 0, the following induced sequence of S modules should be exact. And here is the sequence: 0 goes to f of x, then by f of alpha to f of y, then by f of beta to f of z, and that is it. So now we also see that now the rightmost 0 disappears from the second sequence, so the requirement that the second sequence is exact means that it should be exact at the position of f of x and at the position of f of y. And so there is no requirement on the behavior of f at this position f of z. Here is the first example, the first non-trivial example of a left exact functor. Proposition: for any R module M, the functor of taking R homomorphism from M to blank, this is a functor from R mod to the category of abelian groups. Abelian groups are the same things as Z modules. So this functor is left exact. Indeed, consider a short exact sequence of R modules as in the definition. So 0 goes to x, then by alpha to y, by beta to z, and then to 0. Applying our functor, we have the following sequence. 0 goes to R homs from M to x. Then, using the postcomposition with alpha, we get to R homs from M to y. And then, using postcomposition with beta, we get to R homs from M to z. Since alpha is an injective map, so this sequence is exact, means that alpha is injective. Postcomposition with an injective map sends a non-zero map to a non-zero map. And this implies exactly that this second sequence is exact at the position of R homs from M to x. So it remains to prove that it is also exact at the position of R homs from M to y. So let's prove that. Assume that phi is a homomorphism from M to y, such that if we postcompose it with beta, we get 0. So it's in the kernel of postcomposition with beta. The fact that beta after phi is 0 means exactly that the image of phi belongs to the kernel of beta. But the kernel of beta is exactly the image of alpha because we started originally from a short exact sequence of R modules. And the kernel of alpha is exactly x. And this is again from the exactness of the original sequence. Therefore, phi factors through alpha. And this establishes exactness of the second sequence in the middle position of R homs from M to y, and completes the proof. So now, if we combine this with the description when this hom functor is exact, then we have the following consequence. Homing from any R module M is always a left exact functor, and it is exact if and only if the module M is projective. Let us now discuss the one-sided exactness notions for contravariant functors. Let f be a contravariant functor from R mod to S mod. We call the functor f right exact, provided that for any original short exact sequence of R modules, so 0 goes to x, by alpha to y, by beta to z to 0, the following induced sequence is exact. So we have f of z goes by f of beta to f of y, by f of alpha to f of x, and to 0. The exactness of the sequence means exactness at the positions of f of y and f of x. No requirements of f of z. Similarly, let us define left exact contravariant functors. If f is a contravariant functor from R mod to S mod, then we call it left exact, provided that, starting from an exact sequence of R modules as follows, so 0 goes to x, by alpha to y, by beta to z, and then to 0, the following induced sequence is exact. We start from 0, go to f of z, then by f of beta to f of y, then by f of alpha to f of x, and that's it. No continuation. And again, here, the exactness of the sequence means that it is exact at the positions of f of z and the position of f of y. There is no condition on f of x. Previously, we have shown that taking homs from any R module M is always a left exact covariant functor, and similarly one shows that taking homs into any R module M is always a left exact contravariant functor. And from previous lectures, we know that this functor is exact if and only if M is injective. Now let us make a slight relaxation of the definition, which will also make it more symmetric. Lemma: a functor f from R mod to S mod is right exact if and only if, for any exact sequence of R modules as follows: x goes by alpha to y, goes by beta to z, and then goes to 0. So this is not a short exact sequence because there is nothing before x and there are no conditions on the behavior at x. Sometimes these are called right exact sequences. So if we have a short right exact sequence, then the induced sequence of S modules of the following form. So we have f of x goes by f of alpha to f of y, then by f of beta to f of z, and then to 0. So this sequence should be exact. So starting from a short right exact sequence, applying the functor, we get a short right exact sequence. And here we see how more symmetric this definition is, because we start from the same type of sequences which we get at the end. Note that this description is stronger than the original definition, because of course in any short exact sequence we can just delete 0 and get a right short exact sequence. But in general, starting from a short right exact sequence, there is no reason why alpha should be injective. So it does not come from a short exact sequence in general. So to prove this lemma, we only need to argue that the original definition implies this stronger property. Also note that any right exact functor, which is right exact according to the original definition, preserves surjections. That's clear. So now let us start from a short right exact sequence, as in the formulation of the lemma, and let us replace it by a genuine short exact sequence. Then it will have the following form. So 0 goes to x modulo the kernel of alpha, and then this goes by alpha to y, by beta to z, and then to 0. That's a short exact sequence. And using the original definition, we apply f, which is a right exact functor according to the original definition, and we get an exact sequence of the form f applied to x modulo the kernel of alpha. From here, f of alpha goes to f of y, then f of beta to f of z, and to 0. So this is an exact sequence. Now, since x surjects onto the x modulo the kernel of alpha, and f is right exact, it preserves surjections, we have that f of x surjects onto f of x modulo the kernel of alpha. So we can surject onto the left position here f of x, and get the sequence f of x by f of alpha goes to f of y, by f of beta to f of z goes to 0, and this sequence is exact because this sequence is exact. And this completes our proof. Similarly, we can relax the definition for left exactness. A functor f from R mod to S mod is left exact, if and only if, for any exact sequence of R modules as follows: 0 goes to x, then by alpha to y, and then by beta to z, the induced sequence of S modules is exact, and the induced sequence is 0 goes to f of x, then by f of alpha to f of y, and then by f of beta to f of z. Again, this is a much more symmetric definition when we start from a short left exact sequence and we get a short left exact sequence. And this is proved similarly to the previous lemma. Now we can use this more symmetric characterization of left and right exactness to get the following corollary. First of all, composition of right exact functors is right exact. Indeed, right exact functors are those which send short right exact sequences to short right exact sequences. This is obviously preserved by composition. This requirement is preserved by composition of right exact functors. Similarly, composition of left exact functors is left exact, and composition of exact functors is exact. Similarly, one can show that if we have some one-sided exact functor and we compose it with a contravariant exact functor, the outcome will be a functor which is exact on the other side. So contravariant exact functors, they change the side of exactness. And of course, a functor is exact if and only if it is both right and left exact. Now we can discuss a nice example of a right exact function. Example. Let A be a finite-dimensional associative algebra over a field K. Denote by star the usual contravariant K duality of taking Holmes over K from blank to K. Let M be an A module. Then, as we have already mentioned before, taking Holmes as A modules from blank to M is a left exact contravariant functor from A mod to K vector spaces. Now, since the contravariant endofunctor star is exact, it follows that the covariant functor of first taking A Holmes from blank to M and then taking the K dual star, and this is a covariant functor from A mod to K vector spaces, this covariant functor is right exact. Next, let us discuss one-sided exactness of adjoint functors. Proposition: let f, g be an adjoint pair of functors between R mod and S mod. Then f is right exact and g is left exact. So any left adjoint is right exact and any right adjoint is left exact. Proof. So we will prove that G, the right adjoint, is left exact, and the other proof is similar. By the relaxed description, we only need to show that G sends left exact sequences to left exact sequences. And the left exact sequence is exactly the kernel of the rightmost morphism in this sequence. So if we look at this left exact sequence, then the sequence says exactly that X is the kernel of beta. So left exact sequences are exactly the kernels. Okay, with this in mind, we need to prove that G sends kernels to kernels. And this follows by Yoneda lemma from the computation which will be presented on the next page. And there we will also use that we already know that home functor is left exact, and hence it sends kernels to kernels. So we compute R homes from X to G applied to the kernel of some morphism phi. So now G is right adjoint to F, so we use the adjunction and rewrite this as home over S from f of x to the kernel of phi. And since we already know that home is left exact, we can move kernel out and get that this is a kernel of the morphism obtained by applying homing over S from f of x to the morphism phi. Again, here we use that f is adjoint to G and rewrite this inner home as home over R, this should be R, from X to G of phi. And now again, we use that home commutes with kernels, and we rewrite this as home over R from X to the kernel of G of phi. And here from the Yoneda lemma, we see that the object G of kernel of phi is isomorphic to the object kernel of G of phi. And this is exactly what we needed to prove. And as a final chapter, let us make a brief discussion of the notion of a Grothendieck group. Let A be a finite-dimensional algebra over some field K. Consider the category of finite-dimensional A modules. Definition: the Grothendieck group of this category is the quotient of the free abelian group generated by symbols associated to objects of this category, modulo the relation that the symbol of y should be equal to the symbol of x plus the symbol of z for any exact sequence of the following form. So here x is a submodule of y and z is the corresponding quotient. Note that this makes set theoretic sense. Also, A mod is not a small category. It is essentially small. The isomorphism classes of objects in A mod form as a set. And our relations in particular implies that the symbol of y is equal to the symbol of x if x and y are isomorphic. So this implies that this group makes set-theoretic sense. Well, and it is also easy to see that this group is in fact a free abelian group with a distinguished basis given by the images of the simple A modules in this group. Why is this interesting? It is interesting because the Grothendieck group of A mod is a very good combinatorial tool which allows one to keep track of the composition multiplicities. Indeed, if X is an object in A mod, we can look at the image of X in the Grothendieck group. And so this is an element of the Grothendieck group, and this Grothendieck group is a free abelian group with a distinguished basis of simple modules. So we can write this element in the distinguished basis of simple modules, and the coefficients are exactly the composition multiplicities of X. The composition multiplicities for each simple module in the A module X. And this allows one to use elementary combinatorics and computations to study A modules. Moreover, since exact functors send short exact sequences to short exact sequences, it follows that they induce endomorphisms of the Grothendieck group of A mod. And this allows one to use linear algebra to study functors. So we replace the module category by the Grothendieck group, and that's just an abelian group, and we replace functors by endomorphisms of this group. And these are just endomorphisms, and we can use matrices to study them. In this lecture, we talked about one-side exact functors. They, in general, do not induce endomorphisms of the Grothendieck group, of the module category. But that can be amended by considering, instead of the module category of A modules, the derived category of A modules. But that is already a notion for a new course. Okay, some problems and questions at the end. Problem question 1, prove with all details that the contravariant functor of taking R homes into an R module M is left exact. Problem question 2, prove with all details that the relaxed description of left exact functors is equivalent to the original definition. Problem question 3, prove with all details that composition with a contravariant exact functor changes the side of the exactness. Problem question 4, prove with all details that left adjoints are right exact. And problem question 5, prove with all details that the Grothendieck group of A mod is a free abelian group with a distinguished basis given by simple A modules. Thank you very much, and see you next time.